In a previous module, we have talked about how to compute forces and the moments on structures and machines. So if you could set up an equilibrium equation for forces and the moments, you could find out what other forces and the moments were. In this particular module, we'll be talking about stresses and strains. And the reason we are studying them is because mechanical as well as civil engineers need to know more than just forces and moments acting on the structures and machines. So for example, what you're seeing on the screen is a very standard medical walker that you can purchase at Walmart for about $20-$25. And in this case, let's say an engineer's job is to design this particular walker. Okay. Now, what does it mean to design a walker? Well, we know that it should be able to satisfy certain design constraints. And the foremost of those constraints may be what kind of loading would be applied on this walker. So you could say that, okay, I want this walker to be used by a person who could weigh up to, let's say, 300 pounds. All right, so that means that the design of this walker has to be such that if you applied, let's say, equal load on both sides, 150 pounds, okay, then this walker should be able to take that load. So the questions that sort of come to mind are, what should be the basic geometry of this walker? Now, in this case, you can see that we have sort of two U kind of structure. Here's one U structure and here's the other U structure. And these two U structures are joined by two cross beams. And then we also have cross beams here and here, as well as here and here. So once you decide on a certain topology or geometry of this walker, you have to answer the questions like, what should be the material from which this walker should be made? If you are going to use, let's say, a cylindrical or round tubing, then should they be made of some sort of a metal alloy like aluminum alloy or a steel alloy, or could it be made from wood? You have these questions of what the diameter of these round tubing should be. If you can see sort of over here that these cross beams are not as thick as the leg support over here. So could you have picked maybe a different diameter? So these are all the questions that you have to answer. Now, to be able to answer those questions, you have to bring in a couple of new concepts beyond forces and moments. And those two concepts are concept of a stress and concept of a strain. So a typical walker probably would weigh no more than 7 to 8 pounds and is designed to take a load of a person who could weigh up to 300 pounds. Now, we have done some stress analysis using Autodesk Inventor for a regular walker, and you were seeing some of those results over here. Now, these results were actually produced via a computational analysis tool called finite element analysis, because this is a slightly more complex geometry, so it will be hard to compute it by hand. So essentially, in this case, the entire body is divided into small volume material, and then there are constitutive equations that are solved, which are essentially partial differential equation to get the stresses and the strain on the entire system. So on the left, you are seeing what we call von Mises stresses. And if you are in the red zone, that's high stress. If you're in the blue zone, that's low stress. And of course, you want to make sure that more or less everywhere the stresses are low or below a certain threshold. And what that threshold should be, we'll talk about. So that relates to the properties of the material. On the right hand side, you're seeing the displacement, more or less deformation. So you can see which parts there is more deformation. So in this case, if you find that there is a lot more deformation than is acceptable, because beyond a certain point, this particular walker, certain parts of the walker could fracture, could break, which could be detrimental for a human user, or it could deform to the extent that it is no longer usable in a safe way. So we are designing products, we are designing structures and machines so that they don't fail. So the first question is, how do we define failure? Now, failure could be catastrophic, in which case things could break all of a sudden, or the failure could be something which has deformed to the point that it is not going to regain its original shape, and that means it no longer serves its original purpose. So for example, if you take the shaft in a machine, the shaft, if it deforms too much, it could wobble quite a bit. But that could be a good thing. Most of the structures and the machines, if things deform before they break, they at least give you some telltale sign that things are about to maybe fail and you could replace them, because that may be preferable to catastrophic failure. So I'll give you another example. Let's say we have our diminutive paper clip. Okay, now this paper clip is made of perhaps some aluminum alloy, and it can take a certain amount of load before it will permanently deform, in the sense that it will not regain its shape. So as I apply this loading over here, you can see it tries to regain its shape. In fact, this ability to regain its shape, this springiness, is what we desire, so that it can hold the papers together. Now I can apply a lot more load, and beyond a certain point you will see that it's not going to regain its shape. I could take this entire thing and stretch it out, and if I start to twist it, I can easily break it too. So clearly it has failed in this case. So failure could be fracture, or failure could be deformation, which is not acceptable anymore. Now different materials will respond differently to the kind of loading that you apply on them. So here is another example. I have this material, this is chalk, your regular chalk, and you could actually apply different kinds of loading on it. So I'm going to demonstrate this to you by applying 3 different kinds of loading. So one is that I could apply tension on it. So I could pull at both ends. Okay, so let's see what happens when I pull at both ends, and it fractures. So you know that when you pull it from 2 sides, it is not going to deform at all. There will be no appreciable deformation, at least not what you can see. Okay, so in this case, it's instantaneously broke. This is very different from what happened to the paper clip, because when you apply the loading on it, it essentially was deforming before it fractured. And this is made of a material what we call a ductile material. So it appreciably deforms before it fractures. On the other hand, something like chalk, or even any ceramic or some grades of plastic actually will not give you any signs of deformation before they fracture. So other thing to notice is that when you look at the fracture cross sections, you see they're almost flat. Okay, they're almost flat essentially. Now if you take a ductile material, so imagine if this piece over here, this cylindrical piece over here, was made of some grade of let's say aluminum alloy or steel alloy, and you applied this tensile loading, it would not be a flat cross section over here. It would be what we call a cup and cone kind of structure. So you will have a cone at one end, and you'll have a cup, and the two would fit. Okay, and that happens because when you apply the tensile loading on a ductile material, there is something called necking. On the other hand, you could also design products that you want to fail essentially. Okay, so for example, I have a wired shear over here. Now this wire shear is designed to cut wires, right? So when I apply a certain amount of load from this wire shear on the wire, I actually want this wire to fail, right? So we're designing for the failure. In this case, I want this wire to cut. This is my instrument that should cut this wire. So I have to know something about the material property of this wire and the kind of forces that I can potentially apply so that it would cut it. Now let me take another piece of chalk, and this time instead of pulling it, I'm going to twist it. So see what happens when I twist it at both ends. Now you see the cross section is almost like a helical kind of shape, right? At an angle of 45 degrees, and you can actually tell a lot about the kind of material that you're dealing with, or what kind of loading may have been applied on it by just looking at the failure modes in this case. Another example of another kind of loading would be a bending, right? So I'm going to apply a bending at 2 ends, and you see in this case also we get almost like a flat cross section. So it's almost like the tensile load that we applied. Now the same load on a ductile material will give a different kind of cross section. So I already told you that on a ductile material, if you apply the tension, you'll have a cup and cone kind of a structure. Okay, if you apply torsion, you will actually get a different kind of structure. In fact, for ductile material, it will be almost like a flat surface. So coming back to our walker design over here, you can see that in this case, we have done the analysis for a very high grade of aluminum called aluminum 6061. It has a lot of strength. The mass density is pretty high. So as a result, this particular walker could weigh as much as 40 pounds because we have picked a very strong material, and typically walkers are not made of this kind of material. A third number over here is a yield strength. We'll talk about what the yield strength is, and this is 39 kilo-pound per square inch, and the ultimate tensile strength, which is the highest stress that a material can take, is close to 45 kilopsi. The Young's modulus is 993 kilopsi, and Poisson ratio and shear modulus is something that we'll talk about. So all these numbers that you see over here will make a lot of sense pretty soon.